right, students, so in our very first video in gas laws, we talked about the kinetic molecular theory and those 5 postulates based on the assumptions that we've made about gases. Well, those things were based off of what we call ideal gases, how gases should behave under the right circumstances. But really, we're never quite under those right circumstances. So there are what we call real gases, what actually happens based on the temperatures and pressures in the actual real world. So when you're looking at ideal gases versus real gases, these are some of the things that differentiates one from the other. Now, when you guys have a chance, I want you to go back here and click on this link. She does a hilarious job of showing you guys the difference between ideal gas and real gas. I'm not going to spend time during this video to have you guys watch it, but just watch it. She's a hoot. Anyways, so here's some of the differences between ideal gases and real gases. And so just make sure to jot these down. Notice a couple of big things here. That second little bullet there, the attraction between other molecules. Now, we said that ideally, gases don't experience any intermolecular forces between molecules, but in reality, because you're not under the right conditions, such as the high temperatures and the low pressures, the molecules can experience some sort of attraction between the molecules, especially if they're more polar molecules and they have those dipoles that can pull each other together. The other big point is that last point there about the collisions. We talked about elastic collisions, and elastic collisions are collisions in which they would not lose any energy when they hit each other or they hit the side of the container, but in actuality, in reality, they do and can lose a little bit of energy when they collide. So we spent some time talking about the combined gas law, which is what we would use if we were experiencing changing conditions between a gas, such as if we were heating it from one temperature to another temperature, or if we were going to compress a gas and change the pressure. Well, the ideal gas law tells us some information about that one particular gas under one specific set of conditions. So we call this gas law PIV-NERT. So when I say PIV-NERT, I'm talking about the ideal gas law. It's PV, pressure volume, equals nRT. N is for moles, R is the ideal gas law constant, and this is on the back of your periodic table, so no need to memorize this. It's 0.0821, and then temperature. Okay, now with the ideal gas law, everything has to be in a specific unit in order to use this equation. You have to have pressure in atmospheres, you have to have volume in liters, you have to have temperature in Kelvin. Okay, you have to have those 3 conditions, and it's all based on the units of your ideal gas law constant here. All right, so when we're looking at ideal gas law examples, first off, when you're going through all of the values here, you'll see that we have a volume here, we have a mass, we have a temperature, this is, degrees, and then it's asking us for the pressure. So we know that we have to use PIV-NERT, PV equals nRT, because we only have one for each value. We only have one temperature, we have one volume, we are looking for one pressure. You use the combined gas law when you have 2 temperatures, or you have 2 pressures, or 2 volumes, okay? So we're gonna use PV equals nRT. Now, first off, N stands for moles, not the mass. So we have to convert the mass of oxygen into moles. So we have to have the molar mass down here so we can get our moles of oxygen. So we have 0.6 divided by 32, and that's 0.01875. Now, I don't like to round to sig figs until the very end, okay? So we're looking for pressure. Our volume is 5 liters. Our moles are 0.01875. R stands for the gas law constant at 0.0821. And our temperature has to be in Kelvin, so we have to add 273 to that. So that means we have 295. Now, in order to solve for pressure, we would take our moles, 0.01875, times our ideal gas law, 0.0821, times our temperature in Kelvin. And then we're going to divide that by our volume to get P by itself. Looking at sig figs, we're multiplying and dividing, so our sig figs are going to be based off of whichever one of these has the fewest amount of sig figs, which is our 5 liters. So it means we get 2 sig figs. So our answer would be 0.091. And that is in atmospheres. And if you ever have questions about the units for PV equals nRT and what you're solving for, if you look at the back of your chart, your periodic table, these units are listed there with your gas law constant, and it can tell you what units you would have for volume and temperature and pressure. So let's look at the next example here. How many grams of krypton, so we're looking for the mass, are present in a 600 milliliter volume container at, sorry about this, that's 0 degrees temperature, in which the pressure is 10 atmospheres, and then how many atoms. So again, we only have one of each value, so that means we're going to use our Pivner, PV equals nRT. So we have our pressure, which is 10 atmospheres, and that's the unit that we want it in. Our volume is in milliliters. We have to move that decimal 3 spots to the left in order to convert it into liters. I'm going to keep those zeros here because I want to make sure I have my sig figs correct when I look at my work. I don't have moles yet, so I have to solve for moles. My gas law constant is 0.0821, and then my temperature, don't forget, I have to add 273. So it's 1283. So in order to get N by itself, you would take your 10 times your 0.6 divided by 0.0821 divided by 1283. I'm going to go and use my sig figs at the very end. So my N is, I'm not going to write them all down here, 0.0570. Now remember, I'm going to use my unrounded value in my calculator when I do the next step. I just don't want to write all of those numbers down here. Like I said before in one of my previous videos, I'm lazy. All right, now I know that this is krypton and it's asking for the mass, so I'm going to go ahead and do a mole to gram conversion. So I've got 1 mole of krypton down here. I know that my molar mass is 83.80. I really hope it is because I don't have my periodic table handy right here. So I'm going to multiply that thing by 83.80. Oops. And I would get 4.77 grams of krypton. Now there's a second part, which asks how many atoms is this. So I can go ahead and just do another conversion here, starting with my moles, because that's the easiest to do. And just do a second little conversion going from moles of krypton using Avogadro's number to find my atoms of krypton. So I'm just going to go back and find that number up here, hit enter, multiply by Avogadro's, and round this one to 3 sig figs, so 3.43 times 10 to the 22nd atoms of krypton. into my box. I think I accidentally deleted it. All right. Next example. If I have an unknown quantity of a gas at a pressure of a volume of 31 liters and a temperature of 87 degrees Celsius, how many moles of gas do I have? So again, we only have one of each value, so we're going to use PV equals nRT. But my pressure is in kilopascals. I need to get it into atmospheres. So I have 121.6 kilopascals. I need to do a pressure conversion. So that means I have to have kilopascals down here and atmospheres on the top in order to convert. So 121.6 divided by 101.3, that gives me 1.2 atmospheres. Again, I'm going to use the unrounded value in the calculator though when I go ahead and calculate this. I've got 31 liters. I'm looking for my moles. I've got my ideal gas law constant, 0.0821, and then I've got to add 273 to my temperature, which is 360, because I always have to have my temperature in Kelvin. So I'm going to go back up here to my 1.2 number, highlight it, hit enter, times my 31. To get n by itself, I have to divide by gas law and divide by my temperature. I only get 2 sig figs. So my answer is going to be 1.3 moles of gas. Okay. My last example here, what volume will 20 grams, so that's my mass, of argon occupy at STP? Now remember, STP is telling us some valuable information. It's telling us that we have 1 atmosphere and 0 degrees Celsius, which is 273 Kelvin. Now remember, we're not going to use these constants as sig figs, okay? So first off, we have one of everything. So we have a pressure, we have a temperature, and we have a volume. We're looking for volume. And from mass, we can get moles. So we need to do a quick little gram to mole conversion. So I've got 20 divided by 39.95, and that is 0.5. So then I've got my pressure already, which is 1 atmosphere. I'm doing my PV equals nRT. So I've got 1 of everything. I'm looking for my volume. I have my moles that I just calculated. My ideal gas law is a constant, 0.0821, and my temperature is 273 Kelvin. So when I multiply, I'm going to use my unrounded moles times 0.0821 times 273. I'll divide by 1, which means I don't really have to divide by anything, to get my volume. Now, sig figs, I'm going to base my sig figs off of the 1 measured value that I had, which was the mass. That tells me I have my sig figs, and I get 3 sig figs here. So that means my volume is 11.2 liters, because when you solve for volume using Pivnert, you get your volume in liters. Okay? So that's how you use the ideal gas law equation. If you all have any questions about how to use it, just let me know.